Hello, everybody. Welcome back. I wanted to go over the lab today on the bending of light. Sorry about my background. My room's a little messy here. I've been having some work done at my house. Um, I wanted to go over a little bit of the theory behind the lab first, and then I'll show you kind of how the lab is set up and help walk you through the lab on bending of light. So I'm going to share my screen real quick and bring up my whiteboard. And as you've learned so far in your readings, light is an electromagnetic wave. It is generated due to basically oscillating electrons. They oscillate, they generate an electric field, and therefore they also generate a magnetic field. And those oscillating electric and magnetic fields are what we know as electromagnetic waves. And part of the visible light that we can see is a subset of the electromagnetic wave spectrum. Light can then interact with matter, and it can reflect off of different materials, or it can refract or transmit through different materials. And when it does transmit through, it oftentimes will bend when it transmits through materials. Just to kind of give you a little bit of a heads up here, initially, if you think about light interacting with matter, it can interact with things like conductors, metals, and it can interact with other things, insulators, non-metals. And things appear differently because of the way that light interacts with them. When light interacts with a conductor, metal, for example, let's suppose this is a electromagnetic wave coming in, right? A light wave, EM, electromagnetic wave comes in. If this is a conductor, it's going to, a conductor, as we know, that's a metal that has a lot of free electrons, a lot of valence electrons that are free to move around the material. Those electrons are oscillating, and they re-radiate the light, the electromagnetic field. They oscillate back, they're free to oscillate back and forth, and they re-radiate the light. And the light gets reflected off of the conductor or the metal. The electric field in that electromagnetic wave doesn't really penetrate the conductor. As you learned, inside a conductor, the electric field is zero in electrostatic equilibrium. So most metals reflect all of the light that hits them. And that's why metals appear shiny when you look at them. Now, some metals are different colors because they re-radiate certain color wavelengths of light more than others, like gold or copper look more reddish or gold or yellow, compared to silver that kind of re-radiates all wavelengths of light, so it just kind of looks whitish or silverish. But light doesn't really transmit through conductors. It just reflects off of them. But what happens when light interacts with an insulating material? Glass, water, quartz, other things. Let's suppose this is an insulator, non-metal. Light, an electromagnetic wave comes in and hits this insulating material. It's a non-metal. What we observe happens is that some of the light is reflected, but some of the light is transmitted through. And the amount of light that is reflected versus transmitted through depends upon the properties of that insulator. We won't get into that too much, but we do want to learn about how does the light bend as it passes through this insulator? Does it just go straight through or does it bend? And the answer is that it bends, and we're going to look at how much bending happens when the light passes into an insulator. Now, as you learned, light travels at different speeds in different materials. Um, the speed that a light wave travels, its speed v, um, depends upon the material that it's traveling in. And the speed that it travels is the speed of light c divided by n, which is the index of refraction for the material. So c is the speed of light, and n is the index of refraction, is what we call the index of refraction for the material. So in different materials, the speed of light is different. In air or vacuum, where n is approximately equal to 1 for air or vacuum, the speed of the light is the actual speed of light, 3 times 10 to the 8th meters per second. But in other materials, the speed will be slower. If it's glass, n equals 1.5. And so you can see that if I have 1.5 on the bottom of this fraction, the speed is going to be slower in glass. And so because light travels at different speeds through different materials, that gives rise to the fact that light bends as it travels through different materials. And so what does that look like? I'm going to erase this. So I'm just going to try to draw this as neatly as I can. I should probably just copy a picture in here, but I don't know how to do that with the whiteboard, so you'll just have to bear with me. So let's suppose I have, here's the boundary between the two materials. And let's suppose up here I have just air. And so air has an index of refraction of approximately 1. And let's say down here we have glass. And glass's index of refraction is 1.5. I'm going to draw the wave fronts for the rays of light coming in. So if I have a ray of light that's coming in traveling through the air, this is what we call the light ray. And there are wave fronts, and I'm going to show the crests of the wave fronts here. Okay, and they're always perpendicular to the light ray itself. So it's going to look like this and this and this. And there's many of them. I'm not drawing them all. Okay. So these are like basically like the crests of your light wave coming in, the crests of your electromagnetic wave coming in here. And these crests are occurring at a certain frequency, right? Because light has a certain frequency and a certain wavelength associated with it. And in air, it's traveling at the speed of light. It's traveling very quickly. And so these wave crests are going to be far apart, right? It travels a long distance in a given amount of time, right? It's traveling very quickly. But what happens when it hits this boundary and travels into the glass? Well, as we mentioned, the wave is going to travel slower in the glass. Okay, so these wave fronts are going to end up becoming closer together in the glass because it's not traveling as quickly. It's going to go a shorter distance in the same amount of time. The frequency of the light wave does not change regardless of what medium you're in, right? Light waves are being generated by these electrons, right, in the sun or wherever, and they're oscillating at a given frequency, right? I'm not changing anything about the frequency here. All it is doing is going from one medium to the next, right? So I'm not changing the source of this light wave. I'm not changing its frequency. So the frequency remains the same, but the velocity of the wave changes and the wavelength of the wave changes. And the velocity gets slower in glass that means that the wave doesn't travel as far in the glass in the same amount of time. And so if I were going to draw what actually happens to the wave fronts here, the wave fronts have to get closer together. The frequency has to remain the same. And so the way that would look visually is it's going to look something like this. Do you see how this, it's hard to kind of tell from my picture, but this distance is smaller than this distance. Okay, so the light gets bent in such a way where these wave crests are closer together as compared to these wave crests. And if I draw the ray perpendicular to these wave fronts down here in the glass, do you see that the light ray gets bent a little bit? And in fact, it gets bent closer towards the normal. And the normal is a perpendicular line that passes through the boundary of these two. So if this one's coming in at this angle with respect to this normal perpendicular to the surface, this angle right here we would call theta 2, and it's smaller than theta 1. That means that light is bent towards the normal. This happens when the index of refraction incoming is less than the index of refraction that the light is going into. So light is bent towards the normal when I go from an index of refraction low to a higher index of refraction. And that's because the light is moving at different speeds in the different materials. It's kind of almost like if you've ever looked down at like a marching band, and if they're trying to go around the bend, you have some of them moving a little bit faster than the other ones to keep pace. You can kind of almost think about it that way. The wave fronts are shorter here than they are in the air. And we can do the reverse. I will erase all this. If I'm coming from an index of refraction that's high to low, we see the reverse happen. So let's suppose I'm in glass. The light wave is coming from glass that has an index of refraction of 1.5. Glass is moving, the light is moving slowly in the glass, slower than it would be in regular air. So these wave fronts are closer together. It's not moving as fast in a given period of time because its velocity is smaller inside the glass. When it gets to the boundary, let's say it's going from glass to air. N equals 1. The waves are going to be traveling faster in air because of this relationship. It's now going to be going at the speed of light, 3 times 10 to the 8th meters per second in air. So these wave fronts have to be further apart. And the only way that can happen is if the wave fronts start to look like this. And you can see that this distance between these wave fronts is larger than the distance between these wave fronts. And that gives rise to the light bending away from the normal. So if I draw a normal line perpendicular to the surface, this is theta 1, the incoming light, this is theta 2, the outgoing light. The light is actually bent away from the normal to the surface, so it bends out. And so in this case, theta 1 is actually less than theta 2 because the index of refraction of glass is higher than the index of refraction for the air that it's entering. So that's the general idea why light bends. And so when you look into, say, for example, a aquarium, right? The light from the fish tank inside the aquarium is coming out and reaching your eyes. Things get distorted, right? The fish look closer than they actually are. And the reason for that is because of the bending of light in as it passes through different materials. And so the relationship between the index of refraction and the angle that it comes in versus the angle that it is bent out at is what we call Snell's law. And that is the index of refraction for the incident medium N1 sine theta 1, so the incident angle, is equal to N2. That's the index of refraction of the second material that it passes into, multiplied by sine of theta 2, which is the angle that it refracts in the second material. And so you're going to verify this in the lab today. So I'm going to stop sharing and I'm going to bring up the lab. Okay. So in the lab, you're going to click on, you're just going to be using intro in the lab. And I'll put this away. I'll put this away. When you get to the lab, the first thing you're going to notice is that you have two insulators here, air and glass. And you can turn on your ray and you observe that some of the light is reflected and some of the light is transmitted. And you can see the bending of the light here. You can move this light ray around and see how much bending takes place. And if you actually want to measure it, which you'll be doing in the lab, you can use the little protractor here. So you're always going to measure your angles away from the normal to the surface. So draw a perpendicular line through your surfaces, and the angle that you're going to measure is always from that normal. So the incident angle here would be 45 degrees. The outgoing angle here is a little less than 30. Do you see that? So notice that when I went from air, which has a small index of refraction, to glass, which has a higher index of refraction, the speed of the light traveling into the glass gets reduced and it bends towards the normal to the surface. This angle is going to be smaller. You can flip these around. Let me put glass on the top and air on the bottom. Notice that in this case, when I'm going from an index of refraction that is high to a lower index of refraction, the light is going from a low speed to a higher speed when it goes into air. And so the light bends away from the normal and you have a higher outgoing angle here. I hope that's making sense to everybody. So in the lab, you're going to be looking at Snell's law and applying that in different situations and verifying it. And then you're going to determine a mystery material based upon the amount of bending in it. So let me stop sharing and bring up the lab. In the first part of the lab, you are going to you're going to leave the top material as air and you're going to change the second material in the bottom to glass. And you're going to put your protractor up there to be able to measure the angles. You're going to start at an angle of 30 degrees and you're going to measure the outgoing angle and you're going to take the sine of those angles and from that you can calculate N2. So I'll do a couple rows right here. The incoming angle, the first one I will choose is 30. And maybe the next one I will choose is 45. I won't do all of them, but let me go back to the lab. So the incoming angle should be 30 degrees from the normal for my first trial here. So I want to measure theta 2. So I'm going to bring back the lab again. So I'm going to change this to air on the top, glass on the bottom, and my incoming angle is 30 degrees here. My outgoing angle, let's see. Each of these ticks is 5 degrees. So 5, 10, 15, 16, 17. I'll go with 17 degrees right here. It's always measured from the normal, from this normal to the surface. It's not normal, it's not measured from the surface. It's measured from the normal or perpendicular to the surface. So you're going to measure this one. So the first one I will say is about 17. So I will go back and, sorry, I'm jumping back and forth, but I will type in 17 degrees here. Now let me test it for 45 degrees and see what the outgoing angle is. So notice that the incoming angle is now set at 45. My outgoing angle is 5, 10, 15, 20, 25, 26. 26. Now I'm going to apply Snell's law for this, and to do that, I need to find the sine of the angles, because Snell's law takes the sine of the angles. So sine of theta 1, I'm going to plug that into my calculator, and make sure you're in degree mode, okay, because we're dealing with degrees here. Okay. Sine of theta 1, 30 degrees, is 0.5. Sine of the second angle, 17 degrees, is 0.29. I'll do that for this row as well. And 0.44. Now our goal is to determine N2. We know that N2 was glass, so it should be 1.5. But let's verify that using Snell's law. So I'm just going to write this down real quick. Just going back to my whiteboard. The incident medium that the light was traveling through was air. So N equals 1 for air. Sine of theta 1 in the first trial was 0.50. N2 is what we are trying to determine. And sine of theta 2 was 0.29. Let's solve for N2. 1.7. So it's not exactly right. Let me look at the next trial because it should be 1.5. That might have just been because my angles were a little bit off in the measuring tool. Let me look at my second trial. And let me test it one more time. You can do it multiple times and hopefully you get an average of around 1.5, but if it's okay if it's not exactly close. So again, N1 was air. In my second trial, the sine of theta 1 was 0.71. and 2. Sine of the second angle was 0.44. So in this trial, my value from the lab was 1.6, a little better. Okay. Again, it should be close to 1.5. Some of these might be a little bit off just because of the preciseness of your measurement tool in the simulation itself. But you should be able to verify that Snell's law is accurate in that first part of the lab. In the second part of the lab, you're going to determine the refractive index of a mystery material. So you're going to change the first material to mystery A and the second medium to glass. So that's a known. And you are going to record theta 1 and theta 2 for various angles here. Calculate the sine of both of them in your table. So I'm going to do that really quickly. I'm going to pause the video so you don't have to watch me do that. So hold on. Okay, so I did a few trials with my mystery material. Let me show you what it looks like in the simulation. So you will change the top to mystery material A. You will change the bottom to glass, which has an index of refraction of 1.5. The goal here is to figure out what is the index of refraction for the mystery material, and hopefully knowing that you'll be able to identify what the mystery material is. I found a few different angles of incidence and refraction here. And I didn't do all the trials, but I filled in a few of the table. So these were my angles of incidence and my angles of refraction, and I took the sine of them and I plugged them into the table here. To figure out the mystery material index of refraction, you're asked to plot a graph and determine the slope of the graph, and from the slope you can determine the index of refraction for the mystery material. So let me show you how to set that up. In Excel, I have one column for the sine of theta 1, and I have the second column for the sine of theta 2, the refracted angle. And I want to make a graph where sine of theta 1 is on the y-axis and sine of theta 2 is on the x-axis. So I'm going to insert a graph like we have done in the past, and it should be a scatter plot. And I'm going to right click inside of this graph and select data. We're going to add series, and you're going to highlight x and y values and put them here. So to highlight the x values, which is the sine of theta 2, I'm going to click on this arrow right here and select all of the data that I went on the x-axis, which is right here. And then go back in and click the arrow, and it will bring you back to this little menu. To highlight the y, which is the sine of theta 1, I'm going to click the arrow here and highlight all of these sine theta 1 values. Click the arrow back to get to the menu and click OK. Click OK again. I only have 3 data points. You'll have more because you'll take more data points. I always give my chart a title so I know what it is I'm actually graphing. Label your axes, right? So I always learned that you should have the y-axis versus the x-axis. So it should be sine of angle 1 versus sine of angle 2. That way I know what it is you're plotting. And we want to find the line of best fit through these, calculate the slope, and figure out what the slope represents. So I'm gonna, now anytime you click outside of the graph, your graph or your chart options go away. So if you want to bring the chart options back, you click on the graph and you click on chart design up here. Add chart element, and you want a trend line. It's a linear, looks linear, right? So we're going to click linear. And I want to get the line of best fit through this trend line. So I'm going to double click it. You might have to click over here on the options where it's like the graph here. I don't know why. And then you just click display equation on the chart. If you want to, you can set the intercept to 0. The intercept should be 0 because if the light just comes in at a perpendicular straight in, it's not going to bend at all. You only see the bending happening when it comes in at an angle. But if it's coming straight in, there's no bending. So sine 0 is equal to sine 0. So that's it. So this is your this is your equation for the line of best fit here. So the slope was 0.6525. So what does that mean? Well, Snell's law was n1 sine of theta 1 is equal to n2 sine of theta 2, right? And if I rearrange this a little bit and I do sine of theta 1 divided by sine of theta 2, which is our rise over our run, right? It's our slope of our line here. So this is our slope. That should be equal to index of refraction 2 divided by index of refraction 1. Just rearranging this algebraically. Sine of theta 1 over sine of theta 2 is our slope, right? So our slope of our line should be equal to n2 over n1. The slope of the line that was given, that we figured out here in the graph, was 0.6525. That has to be equal to the second index of refraction, which was glass, right? It went from the mystery material into the glass. So N2 is glass 1.5. And the mystery material is N1, which we're trying to figure out. So if I solve for N1, (2.29) index of refraction. Well, it's basically about 2.3. Okay. That's a pretty high index of refraction. So let's go back and look at our lab again and see what that means. At the end, it gives you a list of the index of refraction for various materials. So my index of refraction was 2.29. So potentially it could have been cubic zirconia, diamond, or cubic zirconia or diamond. I could check which one was closer and make my final decision based upon that. If I had more data points, I might have also gotten closer to one of these as well. But that's your goal, to figure out what was the mystery material and determine the percent error, how close you got to this mystery material. So I hope that's making sense. We see this phenomena every day, right? Whether we're dealing with mirrors, even when we're cutting gemstones to put in our rings, diamonds are cut a certain way because you want the light to refract in them and then refract back out the top surface. So they have to be cut at the right angle. But I hope this little lab video helps work through the lab, and I look forward to seeing all of your results and looking at what your mystery materials were.